Hello, presentation. This is day 3 of Algebra 1, the summer version. So we're going to hit 3 key topics from class today in this video. We're going to talk a little bit about standard form of linear equations, talk a little bit about point-slope form, and then finally ended up with graphing of inequality. So these are our 3 topics. It doesn't cover everything we did in class, nor is this meant to replace class, but it's just some extra explanation and some extra problems that I'll work for you. And so hopefully this is useful to you, and let me know if it's useful to you. Okay, so let's cut over to our sketch pad here, and we're going to talk first about the standard form of a line. So let's look here at the standard form of a line, and the standard form looks like this. So we know that there's a point or a slope-intercept form, and the slope-intercept form, it looks like this: y equals mx plus b, where m is the slope and b is the y-intercept. Okay, and you have this y and this x here that are your variables that can be multiple different values. In fact, usually infinite number of value pairs of x and y's. So let's get rid of that. That's our slope-intercept form. But when you have things in the standard form, it looks like this: ax plus by equals c. And the deal here is that these are your numbers that change, values that change. And the deal with them is that each one of them has to be an integer. An a, b, and c have to be integers, and a is positive. So b and c can be negative, but a must be positive, and then all 3 of them, again, must be integers. So some examples would be, this is the equation of a standard form of a line: 3x plus 2y equals 10. Our a is 3. That's our a. Why can't I could draw my a. There's my a. My b is 2. And my c is 10. Okay, here, this is also a good example. We have a implied 1, so my a is equal to 1. My b, I take my negative, so my b is equal to -2. My a is my implied 1, and my c is 14. Similarly, on this last one, now don't get confused. This is basically the same thing as 8x plus 0y equals -5. So this is a simplified version of the standard form of a line. The standard form of a line still works if we don't have this, or if we don't have this. It still is valid. So 8x plus 0y equals 5. And in this case, our a equals 8. Our b equals 0, and our c equals -5. Now, these examples over here are not standard form. These are not in standard form. And why is that? This is not in standard form because our a is not an integer. So this is not in standard form. I'll show you how to put all of these in standard form here in a second. So that's not. This one is not in standard form. The second one is not in standard form because our a is negative. Remember, a must be positive. So a is negative. And here, so this is not, and this is not in standard form because our x term is on the right, and the x term must be on the left. So how can we turn this into standard form? Well, we can turn this into standard form by multiplying through by 3. So watch what happens if I multiply both sides by 3, which I can do, and I still have the same equation. I get, and I distribute my 3. I get 2x plus 12y equals 24. In fact, this actually isn't in fully standard form because these things need to be simplified if possible. And I can divide them all by 2. So if I divide everything by 2, I get x plus 6y equals 12. And that would be in standard form, where a is 1, b is 6, and c is 12. Here, I can multiply through by -1. Notice what happens if I multiply my left side by -1 and my right side by -1. This is well, my pen isn't working sometimes. -1. So I'm going to multiply this by -1. I'm going to distribute. So I get 4x, -1 times -4x is 4x, minus 2y equals -10. So that's now, these are now correctly in standard form. And this one can be put in standard form. I'm going to subtract 2x from both sides, and I get minus 2x plus 2y equals 9. And it's not, the x term is still, the a is negative, so I have to do my multiply by -1 on both sides. 2x minus 2y equals -9. And now that one's in standard form. Now, why do we care about standard form? So this is what standard form is, how to recognize equations in standard form, but it doesn't tell you why it's useful. Well, one really good reason of why it's useful is it's good for constraint modeling linear equations. It's good. Standard form is good for constraint modeling linear equations. So let's talk about some constraint, what we mean by constraint. So here's an example. Let's explain by example. We have hamburger meat costs $2 per pound. I'm at the grocery store and I have $30. And the question is, how much meat can I buy? Meat is chicken is meat and hamburger. These are both meat. Hamburger and chicken, these are both meat. And the question is, how much can I buy with $30? And there's actually a lot of answers. One thing you can do is you could buy all hamburger and you could buy 15 pounds of hamburger. I'm just, or I could buy how many pounds of chicken? $3 per pound at $30. I could buy 10 pounds of chicken. Those both work. But there's some combinations I can actually buy. And I don't know exactly what those are, but I can graph those solutions. So watch how we do this. And all of these problems are going to work the same way. So the first thing you need to do is you need to look over here and you need to see, well, we want to graph the pounds of chicken versus the pounds of hamburger. So let me move this little chart here a little bit to get it lined up right. Okay, so the first thing we're going to say is, well, the pounds of chicken, we're going to say y, we could say x, but we'll say y is equal to the pounds of chicken. And we did a number of these in class today, so hopefully this isn't totally out of the blue. Y is the pounds of chicken I buy, right? So I could buy 10 pounds of chicken, and that would be my $30, right? And we'll let x equal our pounds of hamburger. Because we don't know. We can buy more or less pounds of hamburger, more or less pounds of chicken. So we're just going to let those be variables. And watch what happens. So now, what is the cost of my chicken at, if I have X pounds? So if I have X pounds of chicken, let's say I have 1 pound of chicken. Let's say I have no pounds of chicken. No, sorry, this is Y pounds. So watch what happens. If I have pounds of chicken. Yeah, let me just write the whole thing out so we can see it. Pounds of chicken. And then let's talk about the cost. Well, if I have 0, it's 0. If I have 1 pound at $3 per pound, it's 3. If it's 2 pounds, it's 6, right? It's times 3, times 3, times 3. So if I have Y pounds of chicken, Y times 3 is 3Y. That's my cost. So we can put 3Y here. That's the cost of Y pounds of chicken. If I tell you Y is 1, you'll tell me 3. If I tell you Y is 3, you'll tell me 9. If I tell you Y is 10, you'll tell me 30. Similarly, 2X is the cost of my hamburger. So then you could say that 2X plus 3Y is equal to my total cost, right? If I spend 3Y on chicken and 2X on hamburger, then 2X plus 3Y is my total cost. And how much can I buy? I can buy 30. So watch this. I'll say, well, 2X plus 3Y equals 30. And that's my equation. Now we'll go back to yesterday and we're going to plot using intercepts, because when I'm in standard form, it's often the key thing to do is graph using intercepts. So the way that we do that is we say, well, we draw our X and our Y and we find our points. And we say, well, when X is 0, what is Y? So if X is 0, then this term goes away, and then Y is 10. And then if my Y term goes away, or my Y term goes away, because Y is 0, then X is 15. You can write that out. You can solve those out if you'd like. Saying 2X plus 3 times 0 equals 30, 2X equals 30, X equals 15. You can write it all out and you can get there if you want. I just kind of went shorthand because we kind of figured out how to do that in class today. Okay, so now we know 2 points on our graph. Well, one is 0, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0, 10. And then this is 2, 4, 6, 8, 10, 12, 14, 16. And here's 15, 0. And here's 0, 10. Now we can graph using intercepts. So let's draw our straight line. Shoot, how come our line disappeared down to 1 point? Let's make it a little fatter. And so these are all of the points where we can buy certain amounts of chicken or hamburger. So let's identify some of those points. Let's see what happens. How about right here? Here, let's check this one out. Anything on this line should work. So let's try them out. 6, 6. How about this one here? 12, 2. Let's see what happened. So this would say, can I buy 6 pounds of chicken? That's our 6 here, and then our 6 pounds of hamburger. And so how much would this cost? This would cost 12. Our 6 pounds of chicken would cost 18, and so there would be our $30. How cool is this? Let's see. Now, can all these points really work? Let's try this out. Well, 12. This one here is 12 pounds of hamburger. That's $24. And then we have here 2 pounds of chicken. Well, that's $6. Again, we have $30. We know that this point works, 15, 0, and 0, 10, because we've already tried those out. So we have a model where anything along this line will tell us how many pounds of chicken and hamburger will give us $30. This, again, is called a constraint problem. I have $30. I can buy 2 things with it, and I can linearly model how much I can buy at any different point for chicken and hamburger. Okay, let's do another problem like this. These, you'll get the hang of these. They'll get pretty easy, but they start off kind of hard. All right, so now I have rectangular tables hold 10 people and circular tables hold 8 people. So I'm having a party with 30 people, right? Party with 80 people. And I need to seat them all. And I can buy rectangular tables, which have, rectangular tables, and this will hold 10 people, and then circular tables, the ones that I can rent, are I can have 8 people. And I can have 10 people at these rectangular ones because I can put people on the end like this. So 10 at the rectangles and 8 at the circulars. So what are some combinations of tables I can rent? So let's figure this out. So let's let X be the number of rectangular tables. Rectangular table number. The number of rectangular tables. And then Y will be the number of circular tables. So let's put this on our graph. Number of rectangular tables. And on the Y, it'll be the number of circular tables. All right, so how many people can I sit at a rectangular table? Equals number of people at rectangular tables. Well, if we can't figure out the formula, let's just draw our graph. Let's see, number of rectangular tables. Let's say it's 0, 1, 2, 3, and then X. And so this will be the number of people at rectangular tables. So if I have 0 rectangular tables, I can have 0 people at the rectangular tables. If I have 1, I can have 10. If I have 2, I have 20. 3, I can have 30. So the answer is times 10. Times 10, times 10. So if I have X rectangular tables, I can have 10 X people, because that's times 10. So 10X is the people at the rectangular tables. And similarly, if we do the same experiment, it will be 8Y equals the number of people at circular tables. So the total number of people I can seat is then 10X plus 8Y, and that's got to equal my 80 people. And so that's my equation. So let's see what we can do. Let's graph using intercepts. X, Y. So now if X is 0, so 10 times 0, 10 times 0, plus 8Y equals 80. So in this case, we're going to solve it, and we'll get Y is 10. Similarly, if Y is 0, I get 10X equals 80, and I get X equals 8. So my 2 points are 0, 10, and 8, 0. And I can say 1, 2, 3, 4, 5, 6, 7, 8. So this is 8, 0. 8 rectangular tables and no circular. 1, 2, 3, 4, 5, 6, 7, 8. I can't fit that by 2, so I'll just go by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10, 0 here. And now if we want to connect our points, 2 points make a straight line, we now have a model for our constraint problem. So let's find some points along this line that seem to work. Maybe this one here. This is 1, 2, 3, 4, and 5. 4 rectangle and 5 circular. 4 rectangle will give me 40. And 5 circular will give me 40 for a total of 80 people. What else can I do? Maybe this point here? No, that's on the halves. That'd be 2.5 rectangle. I can't have half a table. Let's see, 2. No, that won't work. 1. Let's try this point here. This point doesn't look like it's exactly on the right point. So this would be 1 rectangle and 9. This is 9, 1 comma 9. Does that work? Let's see, 1 rectangle will give me 10, and then 9 circular will give me 9 times 72. That'll give me 82 people. So that actually works, but the point isn't exactly on the line, so I don't get exactly 80. So that point isn't exactly on the line. It looks like maybe the only point that is on the line might be 4, 5, 10, 0, and 8, 0. So those might be our only 3 solutions that work with whole numbers, whole integers. Okay, so hopefully this is making some sense to you. And we're going to move along, and we're going to look at point slope form. So the point slope form of a line is very useful when I know a point and a slope. So if I tell you, if I told you the y-intercept and the slope, if I said the y-intercept is 2 and then the slope is 4, you could easily say, put this in slope-intercept form and say, well, y is equal to 4x plus 2. And so that's when you'd use slope-intercept form. But sometimes we get a point that's not a y-intercept, and we have to make an equation out of it. And that's what we're talking about with point-slope form. And that looks like this: y minus y1 equals m times x minus x1. And so an example might be y minus 4 equals 6 times x minus 7. This is an example. Okay, so let's see how we come up with that and why it's true. So let's look at the case where I have a point 3, 2. Point 3, 2 right here. And I have a slope of a half, up 1 over 2. We can label our points here, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so our slope is up 1 over 2, up 1 over 2, up 1 over 2. And so any point on this line, all the points on this line are all xy. Any point can be xy, and that's what we're looking for when we write the equation of the line. We're looking for some equation that has an x and a y in it that will work for every single point on this line, that if you plug the point in, it will make the equation true. So let's look at this. So what do we know is true of any point xy? Well, we know that if we take any point, and we did this in class today too, that any point, that the slope formula must be true. So we know that the slope is equal to y minus y1 over x minus x1. Or, we could say y2 minus y1 equals x2 over x1. So we're going to call this point here our second point. So this is going to be kind of like our x2 and our y2. And this here is going to be our x1 and our y1. Okay. So in our case here, our slope is a half. And that's equal to y2. Now our y2 is, again, x comma y. So our y2 is y. And our y1 is 2. because that's our slope. From here to here, this is y minus 2, this distance here. And our x distance here is x minus 3. Right? So our slope of this line is y minus 2 divided by x minus 3. It's our delta y over our delta x. So again, this is our delta y over our delta x. So our slope equals a half of y minus 2 over x minus 3. Our slope is change in y over change in x. Now I'm going to just do a little manipulation here that's totally legal. So watch what I do. I'm going to multiply both sides by x minus 3. Watch what I do. Both sides multiplied by x minus 3. Now, if I haven't, and so if I multiply fractions, that's like x minus 3 over 1. So if this is the same on the bottom, I can cancel that on the top. And so now I have 1/2 of x minus 3, because I'm going to use the commutative property and put my half in front, just because it's easier to read. And that equals y minus 2. Now I'm going to use my reflexive property of equality and put the y minus 2 on the left. So what's what I do? Y minus 2 equals 1/2 of x minus 3. And that is my point slope form of a line. Now watch, check out what's cool about this. My x, my x coordinate of my point is my 3, and it goes right here with my x. My y coordinate goes right here. And then my slope goes right here. So given a slope and a point, you can always put it in point slope form. Watch what happens. Let me do another one. Let me just do an example right here without having to draw the whole thing out. If I had a slope equal to 3 and a point of 4, 10, the point slope form of this equation is simply y minus my y coordinate equals my slope over or times x minus my x coordinate. And that is the point slope form of a line. Let's do a few more. Okay, so this is kind of the summary up here at the top. What is the equation of a line with m equals 4, slope is 4, containing the point 4, -2? Well, if we got to look at it like, use our equation, we'll say y minus y1, y minus -2. Now, our y1 is -2, so we got to subtract the -2, and that equals our slope over x minus our x coordinate. So y minus a -2 is the same thing as y plus 2 equals 4 times x minus 4. Similarly, let's do the same thing down here. Well, we have y minus -1 equals -2/3 x minus -3. So we get y plus 1 equals -2/3 x plus 3. Now, the other thing we can do is we can convert these into slope-intercept form by simply doing a distribution and doing some other tricks and then rewriting these. So watch how we do that. We say, well, y plus 2 equals 4x minus 16 by distribution. And then we subtract 2 from both sides, and we get y equals 4x minus 18. And this is slope intercept. Again, and this is point slope form. So we have, remember, three forms. We have our standard form, which we learned about earlier, our point-slope form, and our slope-intercept form. Here you can do the same thing. Instead of distribution, I'm actually just going to multiply by 3 first, because that's going to make this thing easier. So I get 3 times y plus 1 equals 3 times negative 2/3 times x plus 3. So watch what this does. This gets rid of my fractions for me. So I get 3y plus 3 equals negative 2 times x plus 3. 3y plus 3 equals negative 2x minus 6. 3y equals negative 2x, subtracting 3 from both sides, minus 9. Now I'm going to divide everything by 3. And I get y equals negative 2/3 x minus 3. Remember, when we separate fractions, it's negative 2x over 3 minus 9 over 3. So minus 9 over 3 is minus 3, and negative 2x over 3 is negative 2/3 times x. Okay, good. Hopefully this is making some sense. So now there's one more application of point-slope form that I want you to look at, and that is finding the equation of a line given 2 points. And to do this, we're going to use the point-slope form, but only after we find the slope, because we don't know the slope quite yet, so we have to find the slope. So if you have 2 points, you find the slope, and then you use one of the points, just like we did on the last slide, to write the equation in point-slope form. And then you can convert that into slope-intercept form if required. So let's see how we do this. So m equals y2 minus y1 over x2 minus x1. So that's equal to 1 minus 3 over 4 minus 3 equals negative 2 over 1 equals negative 2. So that's our slope, negative 2. So now I'm going to use this point here. Now we could use either point, but I'll just use the first one. And so we want y minus y1 equals m times x minus x1. So y minus 1 equals negative 2 times x minus 4. Alternatively, you could have used that first point, and you would have had y minus 3 equals negative 2 times x minus 3. And you say, wait, what's going on? I have two different forms, or two different answers to point-slope form. And the answer is yes. There are as many representations of lines in point-slope form, one for every point on the line. And there's infinite number of points on the line. However, watch what happens if we convert both of them back into slope-intercept form. Now let's convert here. Let's use a different color as we do this. Now we're going to convert to slope-intercept. And this is guaranteed to be unique. The neat thing about slope-intercept form is, one, it gives you the slope and intercept, but it's always unique. So when I convert both of these to slope-intercept, they better be the same thing. So watch what happens. Y minus 1 equals negative 2x plus 8 plus 1 plus 1. Y equals negative 2x plus 9. And here we have y minus 3 equals negative 2x plus 6 plus 3 plus 3. Y equals negative 2x plus 9. Good. Whew. That was close. If that didn't work out, we would have broken all of mathematics. Probably would have caused an earthquake or something. All right, let's move on. Third major topic. That is graphing an inequality. When you graph an inequality, the whole key, there's 4 steps. And it's pretty much, a lot of these are pretty simple steps. So the first is you just identify whether we want a dashed or a solid line. And that means, whether or not the line is included in the answer, right? So greater than or equal to, less than or equal to means solid line, which means the line is part of the answer. A dashed line, less than or greater than, means that the line is not part of the answer. Okay, so you just identify whether you're using a dash or solid. You don't draw anything yet. Then you graph as you would an equality using a dashed or a solid line. So now here's the part where we do the graphing. We actually figure out how to graph, and then we use our dashed or solid line. The third thing we do is then we got to figure out which side of the line includes the answer. Remember your answer is a half plane. So it's not just, so if this was a line, your answer would be, everything on one side of the line. And that's what you call a half plane. So it would be not anything over here, but it would be everything over there. Okay, so let's see how this works. So when we graph this, we say, well, this is slope intercept form. Our slope is 2 and our intercept is 1. So let's put our point here at our y. This is our y-intercept. And then we're going to go up 2 over 1, up 2 over 1, up 2 over 1. Because it's less than or equal to, we're using a solid line here. Okay, we're going to do a solid line. So let's go ahead and draw our line, solid. Okay. Put our arrows to indicate it goes infinitely in either direction. Now, so we've done solid line. Now we're going to find a point not on the line to test whether it's true or not. Okay, so if it's true, it will shade that entire side of the line. So I always like to try the point 0, 0. As long as 0, 0 is not on the line, we're going to test 0, 0. And if it makes it true, if it's true, then we shade same side. So if it's true, we'll shade over here. But if it's false, we shade the other side. Okay, so if 0, 0 makes this true, we'll shade over here. And if 0, 0 makes it false, we'll shade over here. So let's see what happens. So 0, so y is less than or equal to 2x plus 1. So 0 is less than 2 times 0 plus 1. So is 0 less than or equal to 1? Well, the answer is yes. So this works. And it turns out that if one point on one side of the line works, everything over here works. So we're going to shade everything over here. And just to verify that that's true, let's try this point over here. 1, 2, 3, 4, 5, 6, 7. Let's try this point over here, 8, 0. It should work, but let's make sure it works. So does 8, 0 work? Well, 0 is 0 less than or equal to 2 times 8 plus 1. Is 0 less than or equal to 17? And the answer is yes. And to prove to you that everything over here won't work, I'm just going to try another point. Let's try this one. 0, 0, 5. That better not work. Let's see. So we'll put in 5. Is 5 less than or equal to 2 times 0 plus 1? Is 5 less than or equal to 1? The answer is no. So this doesn't work. So that's good. So we have correctly found the right side, the good side of the line to shade. So your answer is everything on the line, because we have a solid line. Every point on here works, as well as everything over here. Now let's graph another inequality. And in this inequality, this is weird. We don't have an x, but that's all right. We know that this is actually the same thing as, y equals 2. We know how to graph that. Let's look. The first thing we need to know is that this is a dashed line, because we have a less than or greater than. So the line is not going to be part of the answer. The way we graph y is greater than, so we're going to graph as we would in equality. So we're going to graph like it's y equals 2. And that turns out to be a horizontal line, as we know, like this. Now we have to figure out whether to shade above or below the line. So let's see. Let's try again our point 0, 0. Well, we're going to test 0, 0 and see if it makes this true. So we got to put a 0 in for x and a 0 in for y. Well, there's no x's in the equation, so we don't have to worry about that. But we'll put a y in for a 0 in for y. So is 0 greater than 2? And the answer is no. 0 is not greater than 2. So we have to shade the other side of the line. So we'll shade up here. And we'll see that makes everything up here makes it true. Let's try this point up here, 0, 7. Well, 7 is our, 7 is our y, so is 7 greater than 2? And the answer is yes. And we know that all the points down here don't make it true. But let's just try one over here, like 3, how about this one, 3, -1. Well, 3 is our x, and our -1 is y. So is -1 greater than 2? And the answer is no. So we correctly have omitted everything that's below this line, and we include everything above the line. If you test any point up here, it will always make this inequality true. So hopefully this was a useful lesson. Just, this isn't meant, these lessons do not replace the learning in class. The lessons are meant just to kind of reinforce and re-explain some of the examples and concepts that we're doing in class, and it is not comprehensive. It does not conclude everything we do, but it should help you get ready for tomorrow's quizzes, as well as maybe allow you to hear something a second time, or slow it down, or play it over again. I do, in these videos, include the most important concepts. Again, not every concept, but the most important ones are included. All right, take it easy. We'll see you tomorrow in class or later in class.